Now let's start on with today's lecture. Today we want to start talking about dictionaries. Okay, and we're going to use IMDb to kind of go through this. What we looked at so far was we used sets to determine how many unique actors or how many unique personnel were on these movies. But now we want to take a different step. What we want to do is, let's say we want some additional information. We don't want to just know how many unique people there are. We also want to know how many movies each person has been in. Well, if we started out with a set, right, we can get all the unique people. And if we could kind of annotate that set with additional information, such as every time we see a person in a movie, keeping count of that person in the movie, keeping count of that movie as an additional entry, well, then we would be working toward this concept of being able to know how many movies an individual's been in. If that makes any sense. Let's look at a list-based solution for this, just to kind of get ourselves started. All right, let's start off from Untitled 14. This is essentially our the same initial code, right? We just enter the IMDb file. We have a list. This time we're going to have a count list. The count list is going to have it's going to have a tuple. Instead of just having a person in here, a name, it's going to have a tuple, and the tuple is going to be the person's name and how many movies they've been in. Right? The name is here, words.strip. Since this is going to be a tuple, we're going to need to write ourselves a for loop. So we can say for t in count list, right? So we'll go through every tuple in count list, right? So for example, this will be a list of tuples, so it might be Hanks, comma, Tom as a string, and then 6 movies, right? And then we'll have more of these going on. So this is what we're going to be storing in our list, right? So we're going to go through every tuple for T in count list. If our tuple, the first part of our tuple, is equal to our name, right, whomever we're up against, well, then we know that this tuple is the unique tuple that contains this person's name. So we can say T sub 1, right, where we're keeping the count, plus equals 1. We'll add 1 to it. We've now seen them getting credit for being in another movie. What do we do if they're not in there? Well, we can't really do anything till we're all the way done with the count list. So we're probably going to need a flag up here that it tells us whether we found them or not. So let's throw a flag, found equals false, right? That'll start out false. When we first get into this loop, we haven't found them. We haven't even looked at anything yet, so we know that we haven't found them. If we come down here, we'll say found equals true, right? If we get into this line, we've incremented them because we saw them in our list. We can mark them as there. If we get all the way through the list without finding them, found is now false still. So we can say if not found, right? This is the case we haven't found them. We started out false. We never saw their name in this tuple. So when we come out, they're not found. So if not found, well, now we have to add them, right? So we'll do a count list dot append, and we're going to want to append is a tuple, right? We're going to want to append a tuple with name, and, well, if this is the first time we've seen them, then they've only been in one movie so far. So we can throw them in as count list 1. And just to kind of give us some idea what's going on, let's go in and use our sleep code. We'll put our start before here. This will allow us to time it. And when we get out of this for loop here at line 12, we'll wow. How many wrong keys can you hit? Right, and now I'm going to go out and steal some code here. We'll just grab this. That'll print out how long it took us. And maybe we want to say upper equals min. Wow. Min. Length of count list. Let's say 100. And all we're going to do is we're going to print out up to 100 values from this list. So for counter in range upper print. And we can make this look a lot nicer, but there's no reason for you guys to sit around and watch me type. You can make it look nicer on your own. Okay, so all we're going to do is we're going to walk through, and for every name, we're going to look for the name as the first entry in our tuple in the existing list. If we find it, we're going to increment the second value, which is going to be how many times we've seen that name in the file. And if we do that, then we found them. We don't have to do anything else. If we get all the way to the end of this loop and we didn't find the name there, that means the name doesn't exist, so we have to add them in. And the first time we add them in, well, that will be their first movie. We're going to do a little timing, and then we're going to do some printing out of the first 100 values. And if I did this right, we should be able to do end equals time.time. After we get rid of a few glitches, I hope we should be able to do this for hanks.text. And tuple does not support item assignment. Sorry, we have to do something here. We have to do count list sub. Oh well. We're going to have to modify this just a little bit because we can't modify tuples. You know what? We don't need to modify tuples. We'll just make this a list instead, a list of lists. We could do this with tuples. It gets a little bit hairier. But we'll just make this a list of lists. Instead of this, we will append on the list, name one. Okay, because those we should be able to modify. Let's see what this does for us. And that I just threw in there when I was trying to fix this. Okay, so that worked. Runs really fast in about 1/1000th of a second for this small file. And it tells us that Jim Hanks appeared in 6, Colin in 10, Bethan in 1, Good old Tom Hanks, he appeared in 41. Zach did too, and everybody else just appeared in one movie. So it looks like it's working on the small case. Let's run this again for the Midland case. Right, and yeah, we're starting to see things slow down just a little bit. Just a little bit. At some point, we should probably put our counter back in here so we can see how fast or not fast we're actually progressing. But I'm going to let that run for a few minutes. And while I do, we're going to go back and start talking about dictionaries. All right. So the problem is that this suffers from the same issue we had in our unique name solution, namely that we have to walk through our accumulation of names. And as that gets long, this line 16, takes longer and longer. It has to be executed more and more times, right? Because we have to set T to be every value in count list. So it gets longer. And the longer it gets, the more time this line takes, and the more time this line takes, the more time and iteration through this loop takes. So we stop being a practical solution and we get slow. And again, I'm going to tell you that this is order of n squared, because the number of unique names is on the same order as the number of items in the list, right? We had like, 26,000 names in that file, and we have what was it, 20,000 unique names. So, it starts taking some time. And in fact, this one took 105 seconds to actually compute this kind of list. And I don't know, we could do something like I'm going to come here, I'm just going to do count list.sort, which will put this into a sorted order, which is going to be good for us. So that way this comes out, instead of having random Kashira or in the order they were in the file, we'll get a repeatable order based on, or we'll get an order based on alphabetic sorting or lexicographical sorting of last name. But essentially this is what we actually want to get. So it would be nice if we had something akin to a set where we could attach additional information to it, right? And that's what we don't actually have here so far. We were able to generate in a list, we could generate this kind of sort, or we could generate this extra data by kind of putting in two values, the name we want to search for and this value. But if we try to put something like that into a set, well, first off, lists can't be put into sets, so we would be back to using a tuple. But then we would also have to know for every individual how many times they had appeared in the set. Otherwise, we couldn't exactly match that tuple. And sets are only fast. You can't do a partial search. You can't search for the first element of a tuple in a set. You have to search for the entirety of the tuple. So the set solution is not really applicable. We need something else. And that brings us to this kind of idea of dictionaries. By the way, I do want to touch on this alternate solution. This is the absolute worst solution you can do. You can also do a solution that's kind of similar, but instead of ever testing, right? Instead of ever testing to see whether name appears in your count list, and instead of keeping count list as a list of lists with the name and the number of times it's appeared, you could just do this Lecture 11 list sorted code that I have here. Just immediately append everything on to the list. Don't bother looking. The list will be as long as your input file. Then sort it. That'll put all the entries, all the names that are identical together. And then you just have to look through your list and look for runs of the same name. And that's all this does. As you start at the first name and you walk through it until you've exhausted all of those names, right? Counting all the while. And once you've found all of the Tom Hanks, for example, or Hanks, Toms, then you move on to Hanks, Bethan, or Hanks, Zach, and look and start this over again, counting how many times Hanks, Zach comes in. So, this is a different solution. This builds a list of the entirety of the input file, sorts it, and then parses out the individual names one after another. You should take a look at this. I'm going to assume that you guys can figure this one out on your own. If you have any questions, I'm happy to talk about it either next class or at the end of this class. But this is an alternate solution, and this is actually dominated by the time required to do the sort, and that is it's not as good as the dictionary as the set. The set is essentially order of 1 or constant time. This is order of n log n, but n log n is a lot better than order of n squared. And if we walk through this one, we can get the same kind of information fairly quickly. About 2.8 seconds to solve this problem. So this is a much faster solution than the list of lists solution. And we'll talk about sorting and how you get to n log n in a later lecture toward the end of the semester. All right, let's go on with where we were. So what we want to do is we want to be able to annotate set data so that the set data can carry along something with it. And it turns out that that's a very useful operation, and it's so useful that we've started calling those dictionaries, and they're fairly standard data structures. So let's look at what a dictionary is like. You have to start off by declaring a dictionary pretty much the same way you would declare a set or some other value, right? So we'll have this Heights dictionary. And then once you have that, a dictionary looks an awful lot like a list. I got to get out my handy-dandy cheat sheet so I know what I'm actually entering in here. And by the way, this is the first way to initialize one. There's also, you can do this as well. That will give you Heights as a dictionary, and that's why you couldn't use this to initialize a set, because that actually creates a dictionary. But once you have a dictionary, you start using notation that looks an awful lot like list notation. So you can come in here with Heights, and you give it a key. A key looks an awful lot like an index, except it's a little bit more flexible. So we can say Belgian horse, for example. And let's say we want to maintain the height of a bunch of weird or different kinds of animals. We can say the height of a Belgian horse is, on average is 162.6. I assume that's centimeters. And we can do the heights of an Indian elephant is 280. There was a time when I could type elephant. Let's say a tiger is 91. And you notice that the notation looks an awful lot like just accessing lists. And a lion is slightly bigger at 97. I don't know that that's true. I always thought lions were smaller than tigers, but I'll believe it. I'm not going to argue with them. And now we can come in here, we can look at heights, and what we see is something like this. Belgian horse, right? Here is what's called the key. This is the value that looks like the index, and here's the value we put in. And here's an Indian elephant, the key, right? And here's the value. Can I get all these on? Yeah, the value we put in. And here's the tiger, that's the key, and here's the value that we put in, and again, lion and the value we put in. And we can ask questions of this, right? This is now essentially a set in these keys. We can have multiple Belgian horses, we can have multiple Indian elephants, but we can't associate a value with a Belgian horse, and we can't associate a value with an Indian elephant. So we can do questions like, we can ask, is a tiger in heights? And because the string tiger is a key, is one of those values in the parentheses that we put in, or in the bracket that we put in, it'll come back and say, true, tiger is in heights. We can ask a question, is a giraffe in heights? Now, we haven't entered a giraffe, so that should tell us, hopefully, false, and it does. So we can ask questions about whether indices, whether these keys are in the dictionary. Then we can also ask something like, is 91.0, right? And 91.0 is one of these values. It's the height of a tiger. And that'll come back and say, no, because we're not looking at the values. All we're doing is looking at the indices. So let's make the distinction here. Dictionaries have two things. They have, essentially the key, right? And if you think about a regular dictionary, is a list of words, and inside that list of words is the definition of the word. Think of the key as the word you're trying to look up, and the definition is the data that you've associated with it. So when you go into a dictionary, you're not looking for example, the word the, because the is there over and over and over again in the description of the words. I mean, what you're looking for is something you're trying to look up, like Indian elephant. Well, all the things you would want to look up are entitled keys. So if we do something like list heights dot keys, that pulls out all of the terms that we're able to look up. And these terms are, of course, called keys. And if we look at something called list heights values, that tells us all the values that have been associated, but it doesn't necessarily tell us, right, these 162 could be repeated. Let's say we have small giraffes in our town. Heights sub giraffe equal what we had, 280 was our largest. Let's say giraffes are only as tall as elephants. Right? So now we have two 280s. We have our keys now include our giraffe. All right. So that's the whole idea of this dictionary. You have these keys, which are things you want to look up, and then you have values which get associated with the keys. There are two initializations, right? We went over those, the two initializations. This looks an awful lot like subscripting a list. It's not. It uses keys instead of integers. And we'll talk about what these keys are and what they can be. In this particular version, keys are strings. And the in method only tests for the presence of a key. We talked about that. And the keys, essentially are sets. They're not ordered. It doesn't matter what order you put the keys in. They come out in whatever order the algorithm wants them to come out. And that's because of this whole concept of hashing. We went over that just quickly. And conceptually, sets are dictionaries without values. All right, so essentially, dictionaries are just sets where we've added information. The set can now carry along additional information. Let's take at least a minute to kind of look at the exercise. In fact, I'm going to give you till 3:30 to kind of look at the exercise, the first exercise, and see if you can work through this. We've done everything on this exercise except for this, which is overwriting a value that's already there. And essentially, whatever value you assign to that dictionary last is the one that holds. This is important, but it's only important for you in terms of getting a submittee grade. Submittee will parse out dictionaries for you. It won't necessarily associate the curly braces with declaring a dictionary, and if you don't declare a dictionary, you're going to lose points on this one. All right, so I'll give you till 15:28. My watch says 15:24 right now. Dictionary key does not have to be a string. We'll go over what the valid values are for a dictionary key. But since I'm telling you that the keys are pretty much the same thing as a set, anything that you can put into a set, the appropriate thing to derive from that is anything you can put into a set. Anything that's hashable can go into the dictionary key. Keys and values, well, you access a value. Let's see. You access a value by doing heights sub tiger, right? So you access a value by using the dictionary name, the square bracket, and then the value of the key. In this case, our values are strings. So that's how you access the values. If you want a list of the keys, it's list heights.keys. Right? That'll get you a list of all the keys that are present in that dictionary. And if you want a list of the values, you can get it with list heights values. But in general, what we're going to do is we're going to get our list of keys, and we're going to use that to walk through the list using, kind of this notation one at a time. No, because a value can be associated with multiple. So the question is, can you access a dictionary's key index given a value? We could probably reverse engineer it from this heights thing, but the issue is that the value is not necessarily unique. So you can see here that we have 280 in there twice. So when you're trying to get back to the index, which 280 do you want, right? Do you want the first one or the second one? I'm getting a report that there might be something wrong with the lecture exercises. Let me see. They worked for me last night, but that's no guarantee that there's not something wrong. Let me pop in here. I mean, it worked for me. Yes, you can do it. Like I said, there are ways to do it, Brody. You can do it for different ways of looking at it. What we would generally do is this is the same as iterating over the keys and checking to see whether the value was correct. So again, there are multiple ways of doing it. We can reverse engineer this, but the goal of a dictionary is to do a fast lookup. This is now a linear right? To do this is an order of n operation for n items in the list. Whereas to look up something using the key to get the value, that's a constant time operation and can be done a lot faster. Okay. Just to answer the thing in the chat. I'm not really sure what's going on with the auto grader that you guys are seeing, but my code works. The question from Russell is there only one value per key in dictionaries? There's one value, but it can be something like a list, which is a container. You can put as many values and many other values in it as you want. Right. So I think Kristen's actually handling these as good as I can handle them, and just as fast. And we are now 15:29, so I'm going to move on.